In this video, we'll be covering the following three topics: bivariate data, correlation coefficient, and sample covariance. Bivariate data is really just data that is in the Cartesian plane. It's in the r squared space. In other words, it has two real values. The values are in the form of ordered pairs, so we'll have an x and a y value for each sample in our data set, and the data can then be plotted in the Cartesian plane. So for instance, if you see down here we have a point A comma B, the A value is going to be on the x-axis and the B value will be on the y-axis. If we plotted our set of data, we would have a scatter plot of all of those points. Correlation coefficient tells us how the x and y data are related to each other in our bivariate data set. The correlation coefficient tells us an indication of the linear relation between the data. As you see on the plot in the previous page, the scatter plots show us a relationship between those two values, the x and y values, and so the scatter plot shows us that relationship graphically on a plot, whereas the correlation coefficient will give us a single number that relates those two values and lets us know how linearly related those parts are, the x data and the y data. The sample covariance is a value that we use or find using both the x and the y data in our bivariate data. So suppose we have a set of data that you see here. There are little n values, and they're all our bivariate data, so we have an x and a y value for each one of those. If you remember, when we did the correlation for a single variable x, we would have like x minus its mean squared, and we would sum all those up and divide by n minus 1. Well, in the sample covariance, we are using both the x and the y data to do this calculation, and so we are taking the x value minus its mean times the y value minus its mean, and we sum up all of those values for the data that we have in that set, and then because it's our sample covariance, we are dividing by n minus 1, n being the number of data values that we have. The sample covariance can be sort of skewed, if you want to call it that, or is influenced by the size of the data. So if we just multiplied our x data by a constant, then the sample covariance would increase or decrease depending on what that constant is. However, the sample correlation coefficient sort of normalizes our sample covariance using the standard deviation of the x and y data. So the sample correlation coefficient is equal to our sample covariance divided by the standard deviation of x and the standard deviation of y. So we would calculate the sample covariance for x and y. We'd also need the sample standard deviation for x and the sample standard deviation for y. The correlation coefficient has some interesting properties that are shown here. The first being that the sample correlation coefficient can only have values between -1 and 1, so it'll never be outside that range. The second property is that if y increases as x increases, so in other words, if we see our plot and it kind of has a positive slope to it, then the sample correlation coefficient will have a positive value. If when we plot the data in a scatter plot it tends to have a negative slope, or y decreases as x increases, then it will have a negative value. The slope itself doesn't really determine the actual value of the correlation coefficient. However, the value, whether the slope is positive or negative, does determine whether or not the correlation coefficient will be positive or negative. And the third property there says that the more x and y are linearly related, the closer r will be to -1 or 1. As we'll see in an example, if they are exactly linear related, then the correlation will be equal to 1 or -1. If it's linearly related and has a positive slope, it'll be 1. And if it's linearly related and has a negative slope, it will be -1. So we'll do an example here. This example is for data that is exactly on a line. These two data are linearly related. So we have the data set is here. We have the equation y equals x. So for whatever value we have for x, we'll have the same value for y. So I just used 3 data points in this example so we can have the calculations be fairly simple. So I've got the data 1, 1, 2, 2, and 3, 3. Those will be the 3 data points that we use to do the calculations. So we're going to find the correlation coefficient, or the sample correlation coefficient, for this data. The means are fairly easy to find for these two data sets. They both have 3 points, 1, 2, and 3, and so the mean is the middle there, or 2. So both the mean of x and the mean of y are equal to 2. We will need the sample standard deviation, so we'll calculate the sample variance using this equation. And you remember that let's say for the x data, we take the x value minus its mean, and then we square it. And then we take and we do that for all the data. So we've got 3 points, and so we have x minus 2, 1 minus 2, 2 minus 2, and 3 minus 2. We square those values each. And then since this is the sample variance, we're dividing by 2 because we have 3 data points. And if we do that, we get 1, and therefore the sample standard deviation is also equal to 1. And because the x data and the y data are identical, we have the same thing for the y data. The sample variance is 1, and therefore the sample standard deviation is 1. Now we need to calculate the sample covariance. Remember, the sample covariance is, let's take a look at the first part here. The sample covariance is the x value minus its mean, in this case 1 minus 2, and times the y value minus its mean. And since they're both 1, we have another 1 minus 2. We do that for each of the values. So we take the x value minus its mean, y value minus its mean. We do that 3 times, multiply and sum. And then because we're doing the sample covariance, we divide by 2. And we also get 1 for that. And once we calculate the correlation coefficient, we have the sample covariance divided by the sample standard deviations for x and y, and those end up being equal to 1, which is exactly what we were expecting, since the data is exactly linearly related. For a data set that isn't quite linearly related, we'll look at, I use the same x values, 1, 2, and 3, but I changed the y data a little bit, 1.2, 1.8, and 3.3, and I got a small sketch over here of the data. So the mean is going to be, for x is going to be 2 again. Y will just sum up the values and divide by 3, and we end up with 2.1 for its mean. So now we're going to go through all the same calculations that we've done before. The standard deviation for x is 1. For y, we take each of the values minus its mean, so the first one would be 1.2 minus 2.1 squared. Do that for all the values and divide by 2. We end up with 1.17 for the sample variance. The sample standard deviation for y, we just take the square root of that and we get 1.0817. For the sample covariance, we take, again, the x values minus its mean, so in this case 1 minus 2, times the y value minus its mean, which is, for the first one, is 1.2 minus 2.1. We do that for all of the values that we have in our data set, divided by the number that we have minus 1, and we get a sample covariance of 1.05. The correlation coefficient will just be that sample covariance divided by the two standard deviations. And notice that we'll end up, when we do that calculation, we end up with 0.9707. So what does that value tell us? Well, it tells us that the data is fairly linearly related, which we were kind of expecting because I didn't change those y values very significantly. It's also positive because the slope of the data tends to be positive, and because it's almost equal to 1, we know that it's going to be on a fairly straight line. Here's some data that I generated and plotted the y values versus x values, or x values versus y values, and the correlation coefficients are at the top of each of the plots. So the first one up here, the correlation coefficient is 1, and notice that the data is exactly on a straight line. The next plot over here to the right, the correlation coefficient is about 0.96, and the data still follows that same trend along that same line, but the data it's not exactly on the line, and so it's fairly linearly related, but not exactly. If we look at the third one, the correlation coefficient is still pretty close to 0.96, but the slope is very different than the one that we looked at just previous. So the slope itself doesn't tell us exactly what the correlation coefficient is going to be. However, we do see that it's still positive. We have a positive value. Now the fourth one, its correlation coefficient is a minus 0.96. Notice that the slope is now negative, and thus the negative value in front of the correlation coefficient. And it looks very similar to the one right above it, but the slope is negative, and therefore the negative sign. The next one down, we have, notice that it's getting more spread out. It's a very similar slope to what we had in the one up here, the upper right hand corner one, but because they're more spread out, the data has a lower correlation coefficient. In this case, it's about 0.48. The last set of data I generated, you can see it's pretty much scattered all around. We don't know really what the trend is, can't really hardly tell there, and the correlation there is almost equal to 0, roughly 0.07, and so the data is almost equal to 0, or at least the correlation coefficient is almost equal to 0.